So people tell that the first thing you should do for a machine learning model, or the easiest way, or the simplest way, or the most lightweight way of doing machine learning is with linear models, linear regression for classification, or linear uh, linear models for regression in general. And I always try to fight that intuition, which I think is flawed, because some people think about tree-based models and ensemble of models and a gradient boosted tree model like an advanced versions, like a maybe too complex compared to logistic regression in terms of complexity and ability to train or capability or to perform inference, how you deploy them. And I think it's just the opposite. Uh, I think it's a misconception. There is one of the things that convinced me the most, and what I have done is confirming that. And they're very much simpler than logistic regression or linear models because first of all they do not make any assumption of the distribution of the features that they use to perform the prediction. With logistic models, with with linear models, you always have the assumption that the features that feed the models are they follow a normal distribution. They are standardized, center with zero mean and one standard deviation. And they look normal. And I found most of the places that they are not. And it's not a wise assumption to take because many times they do not they do not comply to that assumption. On the other hand, tree-based models they mostly uh, kills the need for any feature engineering, for any feature scaling. Uh, Things like multicorrelation or multicollinearity between features, redundant features. It's it's definitely not as harmful as for linear models. If you got linear models and you have correlated features, very easily they could get massive overfitting. But with tree-based models, it's not a big deal. You can waste some of the learning, uh, some of the computations that you have, uh, some of the learning that you spend into the model, but they do not harm you. Uh, while yes, for linear models. So when I say that it probably kills feature engineering using relying in on tree-based models, I say for true. And not only for training but for deploying models, it gets very tricky because with linear models you need to, for this normalization and this feature engineering that you need to have, you need to, for instance, if you want to standardize a feature, you need to keep the standard deviation and the mean of the feature during training somewhere else in order to be accessible during inference and to perform the scaling there, which is not a which is not a blocker because you can rely on pipeline. There are a lot of machine learning frameworks that provide pipelines where feature engineering and all of the transformations into what is the input comes incorporated into a single object, into a model, and the model is is made of several layers: feature engineering, null imputation, standardization, and so on. And finally, you have the last stage of the pipeline, which is applying the logistic regression model. And it all comes into a package where it gets harmonized, and you don't need to store somewhere else the means and the standard deviations and the nulls for the features. But nobody does that. Very few people does that, relying on these pipelines that you can have, for instance, with a scikit-learn or a Spark. Uh, so people store features somewhere else and the means, and then try to map them together into the model, and maybe they get an old version, and it never, most of the times, it never works, and it adds a lot of complexity, which is one of the mm, wrong intuitions about linear models, because they rely on many other things, because they cannot have the assumption that um, because linear models need the assumption that features are standard, are normally distributed. Uh, Feature engineering for tree-based models, very easy. Um, you do not need to scale the feature. You do not need to do any dynamic null value imputation, because they only rely on the ordering of the target relative to the feature. So it's just about the ordering. Uh, so you can, if you want to make null imputation for a feature in a tree-based model, you simply place minus 99.99 for a numerical feature, and it fails. It falls out of the distribution. So the the tree, so the model knows that there is a different value. It's a null, and it learns to treat it differently, and placing it long enough from the rest of the distribution doesn't disrupt the distribution of the feature, because you are not assuming any normality about that. So static um, static null imputation. If you're talking about categorical features, right, you just place like a token, a known token, or anything like that, and it's the same. It's a new category, and it represents the null of the value for that feature. And please do not place empty quotes or something like that, because then it gets confounded with new empty string values, which are very common, but it's different than a null. The same for the numerical values. Please do not fill with zero, because you get a feature representing account of certain values, and you say, okay, let's fill null values with zero. You're actually confounding, and you're achieving the model, saying, okay, this is a zero count. And it's not true. In general, it's just no. You do not know about that. It's different than zero. And with tree-based models, it's very easy to distinguish between a null and a central value. Um, what else to say about tree-based models? Um, they're they're very efficient. Yeah, very efficient, because especially for these new frameworks, where they're not so new, because XGBoost started to be commonly available, let's say 2017, and at that time, it, this is pretty old already, and they're very efficient, because one key thing, um, they rely on gradient descent, and gradient descent, it makes learning and fitting very efficient. Let's think about implementations of random forest, for instance, in Spark. You say, okay, we go for a full cluster, and we perform a random forest with many trees in a very big cluster, and you do that with XGBoost in your local, because Spark, for instance, for random forest, does not perform a gradient descent. You can parallelize, but you cannot get the benefits of doing gradient descent, which you get to a minimum of loss for the algorithm very quickly, probably in the best path to it. And in Spark, with a distributed cluster of random forest, you do not leverage that intelligence to get to the best path to the local minimum or to the global minimum, while doing locally with XGBoost, with gradient boosted trees, uh, it was lightning fast. Uh, and by the way, they're gradient boosted trees in Spark, but they're not extreme. The extreme comes from gradient descent. So it gets parallelized, you get a lot of compute, but you do not get the gains of performing gradient descents to navigate quickly to the minimum of the loss. Um, so these frameworks train really, really fast, even in commodity hardware. Um, what about um, inference? Okay, logistic models or linear models have a strong point there, because it's just doing very easy computations. It's just vector multiplication, matrix multiplication, if you want to think about that. It's very fast, but the trees, the XGBoost family of models is as well really, really fast. Well, to think about extreme gradient boosted trees as advantages in that point. They could be very, very efficient in learning. So you can rely on many way less features. It's you think, okay, maybe it makes not very great difference in the inference of the model itself, but there are many other things that happen before running the inference of the logistic or the tree-based model, because you need to build some features. Uh, and probably I'd say that it's the most expensive part of of the of the compute of the inference in many cases. Um, Not just the calculation of the prediction, but the computation of the features, the computation and the retrieval, because you need to go to lookup tables, or you need to go to a feature store, or you need to go to databases in order to build features out of raw data. Um, that is heavy. Uh, Not only heavy, but slow, and needs a lot of communication. And well, I'm stretching the reasoning, but the idea is that if extreme gradient boosted trees are more efficient, they can get the same level of performance and accuracy with less features, which is many times the case. And that is a strong point for computing and alleviating inference. Not only calculation of the model, but construction and retrieval of features and the data behind the features. So that is a strong case for for tree-based models and stripping gradient boosted trees. Um, they many times say that they're more difficult to interpret, but I don't think it's the case, especially recently. But not in general. It's just a misconception, I'd say, and clutching to familiar ideas. We have the consensus that looking into the coefficients of the linear model is just good enough, and it's clear enough. Sometimes I'd say it's not much better than what we can get as an insight from a tree-based model. We got things like, for instance, Shapley values, Shap. sub library for Python, and model agnostic. Yeah. And and they can deal with any kind of model. Uh, and tree base are not the problem with the trees is the tree one tree is interpretable if it is shallow enough, but with one tree you never get good results. Probably you always get better with averaging across several simpler trees uh, for navigating this trade-off between variance and bias, which is the core of machine learning. So that's the reason why we always rely on several little models. We do the ensemble of them. We do the ensemble of the trees for random forest for trees, and you cannot look and inspect every single tree. But with Shapley values, you can compute the Shapley value of each of the features across all of the trees, across all of the nodes, until the very bottom of the leaves, and you get a very robust idea of which features are contributing. The Shapley value from the game theory, from comparative game theory, has this very interesting thing about the dummy player, the dummy player, the dummy actor. It happens the same. We can interpret that in terms of features, and we have dummy features where they're just present but never add anything if we compute globally. Um, mm, so Shapley value takes about all of the possible combinations of features. What add each feature to any other combinations of the rest of the features. So this makes this combinatorial explosion makes it a strong calculation. It's a heavy calculation, which happens offline, but it makes very robust estimates. Maybe it's more robust than the linear coefficient in a linear model, because basically because we cannot assume most of the times the linearity of these relationships, not the not the normality of the features, nor the linear relationship between a feature and the target. And the coefficient, it's just a coefficient and doesn't take anything further than linear correlation between feature and target, which is poor inside, I'd say, most of the cases. So that's my my takeaway about this. It not it's easier because at the end it doesn't make um, these tree-based models do not take any assumption on the distribution of the features, contrary to linear models. Uh, Feature engineering is um, almost non-existent. Um, Null imputation is statical. It doesn't need to rely on data because you can simply place the minimum value, a value small or high enough in order to fall outside the distribution of the feature. That is statical. That is a static feature imputation. Uh, they're very efficient to train because they rely on gradient descent. Um, they are very lightweight in inference, not just because the um, solid implementation of the frameworks that are available, but as well because being more efficient in learning means that less features are needed, and that alleviates a lot of the computation and the workload that happens in inference in terms of loading and building features. Um, and definitely they're very interpretable, uh, especially in the light of recent techniques like the Shapley values. So uh, doesn't make the case for being not the place to start. I'm talking about tabular data all the time. Assumption here in these thoughts, tabular data. It's not the same. treating audio or sequences or text. It's different realm. But for tabular data, probably the first choice to be the baseline. Um, Even for categorical features, sometimes, okay, maybe this is almost a different topic, but categorical features could be tricky sometimes because um, the high cardinality that sometimes they have. With high cardinality, if you want to perform one hot encoding, it's hard. And so you get too wide a data set if you want hot encode categorical values that have a lot of different values. Uh, Most of the times, it's not an option. And for instance, a cat boost has a very strong and out of the box working um implementation of a target encoding. Target encoding is for each of the categories, you take the mean or some centrality measure of the target. So we're thinking about countries as a feature, as a categorical feature, you, and the success outcome is the target. Some kind of event. You can take the ratio for each of the countries, and it's very tricky because you can overfeed data very easily. So you need to do it in a cross-validated manner. And CatBoost has exactly that. It has like smoothing factors, and for the long tail of very infrequent categories, it has implementations for treating that dynamically in a very well functioning manner. So you do not get a ratio for a country where you have only two data points. Yeah, you bucketize these little countries with or these little buckets into something more um, miscellaneous miscellaneous category where you can um, have more more significant statistics about that bucket. And CatBoost has that out of the box working. You can do it manually, but for instance, for XGBoost or LikeGBM, which are the, all the top free packages for this, as far as I know, it's not out of the box implemented. And they basically cover everything, so they can be the weapon of choice for any tabular dataset that you have. And do not let anybody tell you that this is more complex or heavier or less interpretable than linear models, because they probably just clunch into all assumptions not well revisited in the light of the last years of development in this area for machine learning and tabular data for tree-based models.